Okay, shall we start? Yeah, let's start.
So it's a pleasure to introduce Dr. Arvanitaki. She's a research chair at the Arvanitaki Institute of Theoretical Physics, and she's an expert in particle physics, and her research particularly focuses on designing new experimental observations that can test particle physics beyond the standard model. And she has so far been awarded several prizes, most notably the New Horizons in Physics Prize in 2017 and the Gold Medal in 2022. So today she will talk about her latest work on her cosmic Newtonian background. So
okay, thank you. It's great to see you all again. It's been a while for some of you. So today I'm going to talk to you about the cosmic neutrino background. And I'm going to be talking about not fast neutrinos from supernova, not the fast neutrinos from the sun, but the relic neutrinos that come from the Big Bang. And the beginning, actually, I realize now that my introduction may be too rudimentary, given this talk in the astro and cosmology audience. But yeah, so yeah, the title is self-explanatory for the time being, so I will expand on that. Now, I would also encourage you to interact with questions during the talk. I think it's more important that you get something out of it, even if we don't get through the whole talk. So feel free to just raise your hand and just ask away, okay? Oh, God, yeah. Nothing works now. How do I move it? Okay, great.
So
it's not shaking. Eh?
So you have to be.
Oh, there. Okay, now I have to. Okay, so to talk about. Yeah. It's just that I managed to change it. I'm not going to question it. So the neutrinos that I'm going to be talking about. So this is to understand these neutrinos. Just a reminder, because I know many people don't think about them. In fact, most people ignore them. So we have the Big Bang, universe expanded, hot soup. It started cooling down at some point, to the point where nuclei formed, then have the cosmic microwave background when atoms formed, and you had galaxies, and lo and behold, 14 billion years later, we're here today. Now, for many of you, I suspect the cosmic microwave background is something that you're very familiar with. And it's essentially something that it's the surface of glass scattering. And it's a very important tool because it has managed, so this is a picture from Planck, and basically due to the cosmic microwave background, we've managed to turn cosmology into precision science, okay, which is pretty remarkable. So this is a snapshot of the universe where it was 400,000 years old. And it's an essential tool, as I said, of cosmology. Now, the neutrinos that I'm going to be talking about were formed, it's another type of relic. They were generated at the time where the universe was a fraction of a second old, actually right before the nuclei were formed. And the reason that these guys, so neutrinos are associated with a weak force. And as the name suggests, it's weak. It's much weaker than electromagnetism. And they are associated with radioactivity. So because their interactions are so weak, they decouple from the expansion of the universe. The universe became transparent to them, that is, much earlier than the cosmic microwave background. And that happened when the universe was a fraction of a second old, roughly a temperature of around 3 to 5 MeV. Okay? Today, as the universe has expanded, these guys have become very cold, and they move with a fraction of the speed of light. Now, as I said, this is not in the CMB. We believe they are what explains the N effective that we measure. So we kind of see them indirectly at the CMB. But beyond that, the only neutrinos that most cosmologists or astrophysicists know are the ones from other sources, like supernova, solar neutrinos. And as I said, these guys sit in a very special, these relic neutrinos are very different from all of those. First of all, they're much less energetic. They move with a fraction of the speed of light. So their boost factor is non-existent. Their velocity is between 10 minus 2 and 10 minus 3, if their mass is 0.1 eV. And if you count how many you have, you find that they are also the most abundant neutrino species. Roughly, for each counted neutrinos and antineutrinos, for each flavor, you have 100 per centimeter cube. Overall, they have number density, if you count all three flavors, that is slightly less than the number density of the CMB photons. Their temperature is about 2 Kelvin, just a bit less than the CMB photons. They follow, the interesting thing is because they decoupled from the thermal path of the universe, when they were very relativistic, even today, they follow a relativistic Fermi-Dirac distribution, which actually affects their properties quite a bit. Even if they are non-relativistic particles whose phase space obeys a relativistic Fermi-Dirac distribution. So what that fixes is not the average energy, the temperature. It determines the average momentum of these guys. Okay, so the average momentum is roughly a few times the temperature. And in the standard model, we expect that there is roughly equal numbers of neutrinos and antineutrinos, similar to the baryon asymmetry. This is not a number actually that we have measured. What we have measured is the baryon asymmetry. We know how many baryons and antibaryons there are relative to each other. So in fact, cosmologically, experimentally, we have not constrained this number too much. But the traditional, if you take any standard model cosmology, the most naive expectation is that the baryon asymmetry matches the neutrino-antineutrino asymmetry. And just for the particle physicists in the room, I'm going to be sticking with Dirac neutrinos. You're going to ask me about Majoranians afterwards. That's why I'll be talking about neutrinos and antineutrinos all the time. Okay. So why is it important? I think in an audience like this, probably this is not necessary, but just to remind you that this, if we were to detect these guys, we will get a snapshot of the universe, the earliest snapshot we'll be able to get till today. Okay, and this is part of lambda CDM. It's not an exotic component. So it's very important to remember. The other thing, the neutrinos, they are a crucial part of the standard model, but because they interact so weakly, we don't really know many of the properties. So there are 3 flavors, but there are 7+ parameters that we haven't measured to the same accuracy many times as the other standard model parameters. So it's a largely unexplored part of the theory as we know it. So now, I made a nice analogy with the CMB, so then the question is, why haven't we seen it yet? Why is it so hard to see? And usually the way we are used to detecting things in particle physics is through scattering. So you have a particle comes into your detector, kicks something, deposits some energy, and then you see that energy. Now, because these guys are so slow, this interaction cross-section is tiny. And it's also proportional to their coupling squared, which is also very small. So, yeah, basically it's a losing game. Like if you calculate, I mean, if you have something that was in thermal equilibrium when the universe was 1 MeV in temperature, a few MeV in temperature, today they can they can cross the entire universe without interacting, not even once, or scattering not once, okay? Now, there are ways to circumvent their slowness. So there is an idea, there is one single idea, an experimental proposal, to detect the cosmic neutrino background in a laboratory setting. This goes by the name of Ptolemy, and it's based on the following idea. If I have a tritium nucleus, it can absorb a relic neutrino and convert to helium and an electron. Now, this cross-section, because this is an exothermic process, this is enhanced by the available energy that you have. Nevertheless, you still have to fight a huge standard model background because the tritium has a lifetime of 12 years, so it will decay on its own with a much higher rate. So Ptolemy is a very brave proposal, so based on this idea. Now, in principle, because these guys are so low energy, they have macroscopic wavelengths. Their wavelength, the Broglie's wavelength is between 2 and 4 millimeters. So you can say, oh, I can couple coherently and scatter coherently over a 2 or 4 millimeter object. Nevertheless, you can do that, and the cross-section is large, but the momentum you impart is so small that it's so hard, it's impossible to detect. Okay? So scattering can give you an avenue, but it's still very hard. Now, the question is there a way to do better? So scattering gives you, as I said, cross with a cross-section, with a coupling square. There is a process, though, that just is proportional to the coupling, and that is refraction. So that happens because everything refracts. Electrons refract, neutrons refract, light refracts, as we know, right? And that happens because when waves propagate, every particle wave that propagates through matter will feel and can interact with it, will feel an interaction potential. So the fact that it can feel an interaction potential, it will change the kinetic energy of the wave inside the medium. So this is basically what refraction is. In other words, if I were to put, vice versa, if I were to put an atom inside the neutrino background, it will refract from it, meaning it will feel a small energy shift. Okay? How small is that energy shift? So that energy shift depends on the Fermi's constant, which is the coupling strength of the neutrinos, the charge, or the weak charge of the atom, basically it grows with the atomic number of the atom, and the difference between neutrinos and antineutrinos, okay? So the first thing you say, okay, I have this atom moving through the neutrino wind, can it feel anything? Can it feel a force? And the force will be, the first force you will think about is the gradient of the density, of the energy density, of the energy shift. And the problem is that if you're in a uniform background, because the gradients of the neutrino background are so small, this will be essentially zero. So if you have some uniform density, it will give you zero force. Apparently, this was a big deal because it actually stopped all detection efforts, all detection proposals of these neutrinos back in the 70s or 80s on their tracks based on this. And there were two papers that point this could, something that in retrospect could be obvious, wasn't obvious at the time. Now, there is one effect though that remains non-zero, and that is the interaction of the cosmic neutrino background with spins. So if I have a spin and it's placed in the neutrino wind, the up and down, spin pointing up and spin pointing down, will have an energy, there will be an energy splitting between them. Now again, very small number, 10 minus 47 eV. The smallest thing we've measured on the lab so far is 10 minus 25 eV, so not very close, not seen anytime soon. Now, there is secretly, it's not just the uniformity of the density, all these interactions are proportional to the neutrino and neutrino symmetry. So this is if this is 10 to the minus 9, this is what gives you 10 minus 47 eV, okay? So what I'm gonna be talking about is a new effect that actually goes like the square root of the coupling. So we have the cross-section, because it was coupling squared, very small, refraction, coupling, proportion to coupling, but still really small. And now I'm going to show you something that in principle goes like the square root of the coupling, which if you have something less than 1, always helps, okay, to take the square root of that. And that happens due to reflection of these neutrinos from the surface of the Earth, okay? And that enhances the asymmetry of locally the neutrino-antineutrino asymmetry and causes inhomogeneities close to the Earth's surface. So the idea is the following. So this is a very nice picture. If I have the outside the Earth and the inside the Earth, I can depict, let's depict neutrinos the way we depict light in optics as the rays. So if you have electron antineutrinos and muon and tau neutrinos, they are attracted. The potential that they feel as they go through the Earth is attractive. So the rays that you would draw, as they cross the surface, they move away from the surface. And this is highly exaggerated, okay? Now, if you have electron neutrinos and muon and tau antineutrinos, because those are the ones that are repelled. So if they are repelled, they need to slow down inside the Earth. And what happens is this means that these rays move closer and closer to the surface. Eventually, they'll come at such grazing incidence that they will bounce off the surface. They cannot penetrate the interior of the Earth. So this traffic jam right here is what causes their excess. Now let's go into more detail how that arises. So the interaction energy of neutrinos with matter is determined, if you think about refraction and reflection, we need to define an index of refraction. So the difference of the index of refraction from 1 for neutrinos, which is a very small number, basically measures the difference of momenta of neutrinos inside the material versus outside, okay? Or more precisely, it measures the interaction energy inside the material relative to the kinetic energy that they have. And for cosmic neutrinos, this is 10⁻⁸, 10⁻⁷. Now, just to give you a comparative measure, if I were to do this for solar neutrinos or anything like that, this would be at least 10 orders of magnitude smaller. Okay, so now you understand that fast doesn't help here, slow is good. So this potential, again, is determined by the Fermi constant, the density of atoms in matter, and then the weak charge, which depends on the flavor of the neutrino. Okay? Now, just to keep it simple, I will always, whenever I say, I will stick to electron neutrinos, and I will say, whenever I say neutrinos, I mean the ones that get repelled, and whenever I say antineutrinos, I mean the ones that are attractive. Okay? So just in terms of numbers, this interaction is between 10⁻⁵ and 10⁻⁷ eV. And if you compare to the kinetic energy here, which is roughly 10⁻⁶ eV for a mass of 0.1 eV, you get basically this number right here. Okay? So now, how do we calculate the behavior of these neutrinos as they hit the Earth? First of all, the Earth sets up a huge spherical potential well for these neutrinos. And to start with, let's assume the problem is one-dimensional. So if I would have something that looks like this. I have outside the Earth and inside the Earth. For the wavelengths that we're talking about, the Earth is basically infinite size, okay? So what you have, let's say you have, for the typical neutrino, the energy is so much higher than this potential barrier that nothing happens to the wave. Okay? Not much happens. There is some tiny reflected component, but most of it just goes through. So they don't feel much. Now, if the energy is small, and in one dimension, all you require, if the kinetic energy is less or equal than the potential barrier, then the wave cannot penetrate inside the material. It's a classically inaccessible region, and the whole wave gets reflected back. There is a small penetration to the classically inaccessible region because of quantum mechanics or wave dynamics. And this is what is known, it's also known in optics as the evanescent wave. This is the wave that leaks inside the material when light gets reflected from a surface. Now, in one dimension, this is a very small number. So this is a 10⁻⁷, 10⁻⁸ fraction of neutrinos. So it's tiny. But a very interesting thing happens because you have two dimensions. Now, when you have two dimensions or more, 3 dimensions, like what we do, and you scatter off an angle, now you can come in at an angle. You can scatter off at an angle. What matters now is the momentum perpendicular to the surface, or to determines the dynamics. So because I have translational invariance parallel to the surface, the momentum parallel to the surface never changes. So it doesn't affect the dynamics. So the thing that's sensitive to the interaction potential is this perpendicular momentum. So now the requirement from the reflection that we saw before becomes that the momentum perpendicular to perpendicular to the surface is less than the interaction potential. And then you see that you get a critical momentum perpendicular to the surface that can give you reflection that goes like the square root of the interaction potential. So it's proportional to the square root of G Fermi. And if you convert it in wave number units, this is 1/3 meters. Okay? So it's a humanly sized scale. It's not astrophysical scale, but it's a humanly sized scale. So this is exactly this reflection of this fraction of neutrinos that have momentum perpendicular to the surface less than this is what makes them bounce back. Okay? And this is what creates the traffic jams and gives you the excess. Now, how much is this excess? This excess is determined by how many neutrinos can come in this critical angle, so which is just the, yes, question? Oh, someone is talking outside. Okay, so the critical angle is the amount of neutrinos I get reflected is the momentum perpendicular to the surface divided by the overall momentum. So this is actually a fraction of 10 to the minus 4, which grows like the square root of the neutrino mass. And 0.1 EV is a number that I took basically from the sum of neutrino masses constrained from astrophysics. Okay? So now this 10 to the minus 4 is much larger than the momentum, the fraction that you expect in the standard model. The expectation that you got is 10 to the minus 9. So this is a 5 order of magnitude enhancement, and it happens over this region of 3 meters that's set off by the evanescent wave. And this is a plot that shows this distribution in logarithmic scale. Outside the Earth is here, inside the Earth is here, for different neutrino masses, including possible clustering effects. Okay, heavier neutrinos can cluster, for example, at 0.8 eV, but 0.1 eV and below, the clustering effects are not that important. And you can get a large enhancement in local neutrino to neutrino symmetry relative to the standard model expectation. Now, I should say though, 0.8 eV is very optimistic because this is just using the Catherine bound and ignoring cosmological constraints, which I think is very naive. I would say that this is very optimistic. This is actually more realistic and below here. The great thing is because we've measured from neutrino oscillations, we've measured the mass differences. So we know there is at least one neutrino that's heavier than this. So the interesting thing for neutrinos is, in fact, we've constrained the parameter space within a factor of almost 2 or 3. It's really cool. So if you were to summarize, if you were to take a slice of the Earth, what you would expect to see is a neutrino excess close to the surface at a roughly 3 meter zone above and below the surface. Okay? So now this raises up new possibilities for cosmic neutrino detection, namely what I was telling you before. Now you can have a gradient in the interaction axis. So now there's going to be a force. The force is really small though. Okay? So it's far away, at least 3 orders of magnitude from the craziest thing I can imagine. Okay? And this is really crazy what I can imagine. So experimentally is orders and orders of magnitude away. So the question we asked ourselves is, can we actually do better than the Earth? So can we use the fact that these neutrinos have a relatively sizable, I mean, it's not breaking any records, but this interaction potential is in fact is very important for them. So can we use it to get a bigger signal? And this is what we think. We think that you can. So you can actually create a diffraction gradient for them, we think. So this is the design. I'll tell you roughly how it works. So you take rods of width, characteristic width W and length L, and you put them on the surface of the sphere. This is not drawn to scale. These things are much thinner and longer, okay? And as they go through these rods, they diffract and they create an excess around the center. So this takes advantage basically of the wave nature of the neutrinos. Otherwise, this wouldn't be possible at all. Okay? So now let's see how this works. So you take, let's take a rod. Material can be iron, and we can discuss later what it can be. Let's imagine it's an iron rod. So now I have a neutrino wave that comes in paraxially, okay, parallel to the axis of this. So after it has gone through the rod, to a very good approximation, if the dimensions of the rod are large enough relative to the wavelength, you can approximate the wave at the exit point here with the same wave as it was before times an additional phase, which is the wavelength of the neutrino, the difference of the index of refraction from one times the length of the rod. Okay, so the wave here has accumulated a phase. Now the question is, what is the wave that it produces at a distance d away? And the interesting thing about this, actually, we know how to do this for a really, really long time, how to calculate this. And if you remember your optics class, this goes by the name of Kirchhoff's integral theorem. It tells you that if I know the value of a wave on a closed surface, I can evaluate the wave anywhere inside the surface as long as it obeys a wave equation. And basically, it is equivalent to Hoyen's principle. Oh, I should say, yeah, which from the 17th century, okay? So basically what happens is you treat each point as an emitter of, on the surface as an emitter of spherical waves, and the wave inside the surface, anywhere inside this volume, is the product of the interference of these emitters from the surface, okay? And the cool thing about this is that Hoyens came up with it. This is the essence of the Kirchhoff integral theorem. Came up with it 200 years before Kirchhoff, and he did it without any algebra. All he did was observe that waves can go, like waves on the surface of water, can actually go around corners. So he postulated that if I have a plane wave, the surface of a wave I can approximate with a meter of spherical waves, which is remarkable. So now we do the same. So we have the wave, goes through the rod, it acquires a phase. Now what we do is we need to take the partial waves emitted, the spherical waves emitted from the front here, and interfere them a certain distance away. But now you see what happens. You see that there is a certain distance away where the partial waves emitted from the front of the rod will interfere constructively. And if you run the map, you will see that that happens at a distance of w squared over the wavelength away. That's basically the idea. So this is diffraction. So the phase comes because the wave accumulates a phase as it goes through the rod. And this is basically diffraction from an opening. So this is what causes this diffraction pattern right here. And you get an excess of whatever neutrino or antineutrino has an index of refraction larger than 1 inside the material. Okay? So the width of the excess is set by the opening, and it gets diffused, it diffuses out as you go further away. If you go to infinity, this goes to 0. If you make the wavelength really small, the distance where you get interference effects goes to infinity. So then you see that this wouldn't be possible if the neutrinos didn't have a macroscopic wavelength. And in fact, for the things that we imagine, this is a few meters long, for example, and the width of this is like tens of centimeters. So still much larger than the wavelength, macroscopic. This is a more, I'd say, mathematical depiction of what the asymmetry is. So you get, as I said, the X species for which the index of refraction is larger than 0. And this is a perpendicular, so if I were to cut the wave like this is the type of pattern that I would see. Now, the important thing is, of course, neutrinos are not they're not perfect. So first of all, they don't come in a single frequency, okay? So the first thing you have to do, you have to average over the momentum, integrate over the momentum. And it looks like, at least if you integrate over the things that come from one direction, then you get a similar, the effect gets suppressed, but still remains. So it's roughly of order the phase that you accumulate inside the material. So now, the question is though, there's another defect that these neutrinos have. They are not like sunlight. Sunlight has a thermal distribution too, but it's unidirectional. So we can take a simple lens and focus it. So we can do geometric optics with it, it's perfectly nice. For these guys, we cannot do that. So we actually have to take into account somehow that they come from all directions. So this is where putting the rods on the surface of the sphere came. And you place them in such a distance so that the optimal interference pattern appears close to the center. And then you have to take into account that the fact that most of the time, the waves are incident in between the two rods. So at an angle. Now, and this is a tricky part, and this is the part that we actually, and you get a different pattern. So now the interference pattern gets a bit of axis shifted. And of course, we still worry that there is the worry that if I average over angles, then the effect will cancel somehow. So for that, I did several checks. I took the same, I added more rods around this. I did a 2D exact analog. So the key point is that this structure is periodic. So you need to average over things that are incident within the periodicity solid angle. And if I've done my calculations correctly, it doesn't look like the thing is averaging out. So now the question is, how does it look like if you average over angles? Now, before I do that, I will have to show you, so this is, I'll give you specific examples that use specific materials. So this is a summary of the indices of refraction, how different the index of refractions per month for different material. So you see here water, rock, or dirt. Now, favorite stuff, depleted uranium, great stuff, very dense, useless to many people. Slightly radioactive, not bad for this because this thing doesn't have to be engineered in any way, doesn't have to be instrumented, okay? So don't worry about that. Gold and tungsten are even better, but very expensive. Iron is great. It's a good balance between availability because iron we produce. Actually, iron is the most thing what we most produce on Earth. You look at iron is easy to produce. So you can make big structures out of iron. Of course, there's lead and mercury, but these are rarer than this. So turns out that if you run the numbers, you can take the depleted uranium stockpile of the US and turn it into a 30-meter structure. So it's a good, it's not clear how much that would cost. So, but anyway, so we took different material, different sizes, 2 meters, 10 meters, 100 meters, to see what we will get. And these are the parameters, okay? So it turns out you need a little gap between the things. So I've made approximation. This parameter should be taken with a grain of salt. In reality, someone needs to do a full wave calculation of this structure to see exactly what you will get. And this is the asymmetry that you get for the different parameters at the center of the gradient after you average over angles. Okay. So So here you see for a 2-meter uranium. Now, the key point is already it looks like a structure that is 2 meters in size, built out of some dense material, can be better than the effects that we saw from the Earth. If you go to 100 meters, then you gain another factor of 100. So the bigger you make it, the better it is. So now, okay, so the question that everyone asks me is, okay, what have you done? Okay, what have you guys achieved? Because, and I'll tell you the story of this line of research. So every particle physicist knows, as a young graduate student, their advisor will probably tell them, can you think of the way to detect the cosmic neutrino background? So you go directly to think of ways to detect it, and you get disheartened very quickly because whatever you calculate is always so small. So you very quickly get discouraged. So we decided, just for peace of mind, so before we go and jump into new ways to detect them, can we understand how they behave? Can we find any interesting behavior that can enhance the signals that we expect? So this is the idea of we factorize the problems in our head into manipulations versus detection. But I mean, in reality, we always had a detection scheme in our minds. And I will give you a rough idea, even though this is not a fully fledged experimental proposal by any means. So the idea would be the following. Now that I've created a large gradient of the neutrino asymmetry, I can go to the center of the structure and place a mass there. That mass, because it feels interaction energy with the gradient of the interaction energy between the neutrinos and the mass, will give you a force on the mass. So I can try to build an experiment that will detect that force. Now, if I were to take two masses and connect them with a rod, because this force depends on composition, I would have built a torsion balance experiment that people use to test the equivalence principle. So this is a very important thing. This force is composition dependent. So it, in principle, violates the equivalence principle. Okay? So that's the vague idea. And now you can calculate the force, and you find something really small. It's 10 to minus 28 Newton. Just to give you an idea, this is like 100 to 1,000 times lighter than the mass of a carbon atom, the weight of a carbon atom. Okay? So this is really, really small. But now we have something that's much bigger than we were expecting, than the Earth, and much bigger than you had from coherent scattering, because you can turn the coherent scattering estimate into a force. So it's bigger than what we had. Now, this is a plot similar to what I showed you before, where you have the neutrino mass on one axis, and this is a force multiplied by 10 to the 25 and in newtons. So this is 10 to the minus 28. This is 10 to the minus 25 up there in a log scale. And here you get much higher for 0.8, again, because you get clustering. Okay, so you have higher densities. Now, as I said, I expect this lower range of this plot to be more reasonable. So this is this part of the plot is extremely optimistic. Okay? But if you run, as a good theorist, what I can do is calculate what the standard quantum limit of detection is in a 10 centimeter size piece of material. And I find now that this force becomes bigger than that, for parameters that are similar that they use in torsion balance experiments, okay? If I were to put those in a standard quantum limit, this is what I will get. Now, disclaimers. First of all, the poor torsion balance people are not limited by the standard quantum limit. They're actually limited by systematics. The fact that if someone walks by, there is a force from gravity, not anything else, not electromagnetic, no nothing, just the gravity of the person. The mountain shakes next to the experiment, there is a force. So the question now becomes, how do you perform this force measurement so that you avoid all those systematics? And it looks like the direction we're headed, and this is what we're exploring now. First of all, we have a structure, right? So we create a man-made structure, we can actually mechanize it. So we can think about moving. Now you're telling me how fast can you move something that's so big? Well, you don't have to move it very fast because the structure is periodic. So if it has n segments and you move it with a frequency, with the angular frequency omega, then the actual frequency of the signal is n times omega. Okay? So now we can imagine pushing it in a regime. So if you move something with a millihertz, the eventual frequency is a hertz. So it makes things much better. Okay? Now there's still other issues. Like for example, if I start moving this huge structure, there's gravitational interaction of the structure itself with the mass that you have in there. So these are things that we're in the process of estimating. So the good news is, yes, question, yeah?
Yeah, what's the aspect ratio of the rods? What's the length?
Oh, it's 1%.
What's the,
How well can you align them?
Well, and just, will the rod sag under its own weight?
Yeah, good. So you need to do what think. So actually, when I wanted to answer that question, I went on a Google search and talk about architectural requirements on high skyscrapers, right? So they're building the kilometer tower in the Emirates. So it's within architectural tolerances. So things have to be aligned within 1%. So that's not so bad. So you can do that. Even if they sag, you need to put support structures in between, and that doesn't affect the signal if you have support structures, right? It doesn't have to be filled with material. It's just you need appropriate support structures, which can be a lighter material in between. It doesn't have to be the same.
Can you help me understand where this 1% alignment comes from? Because naively, I would expect any asymmetry in the mass distribution to have a gravitational force. So you would need your...
No, the gravitational force is another issue. I'm talking about whether, what do I do to make sure that I don't smear out the asymmetry from the neutrinos that I get, okay? The gravitational thing, it's not, this 1% is not related with the gravity at all. This 1% is related with the tolerances to actually get the neutrino symmetry. The gravitational force I haven't estimated. I don't know how big it will be. We are in the process of calculating.
Thank you.
I'm afraid it will be too big, but there is, so the hope is, now I'll tell you now, the fear where everything can fail. So if you have a closed shell, mass shell, the field inside is exactly 0. Okay, there's no force. Now the question is, because we have created like a perforated sphere, how bad does that undo the cancellation? Would we make it very bad? Hopefully, because it's 1/r potential, it doesn't make it so bad. So, but this is what we're in the process of calculating, actually. Yeah, so this 1% is just for the neutrino side. It has nothing to do, the gravity will always be there. Question is, how small can we make that gravitational background? Because naively, if we were to calculate the force from that mass, is big. It's much bigger than the signal you want to detect. Okay. Good. So now the other thing you could do, we think, is dark matter. And for that, we have an excellent candidate, and I can talk about it actually. So we have axioms. So in particular, the QCD axiom. So the axioms have been proposed to solve a fundamental problem, which is to explain the smallness of the electric dipole moment of the neutron. So for elementary particles, electric dipole moments violate both parity and time reversal. Because for elementary particles, the dipole moment needs to be aligned with the spin. So if you apply parity, it flips the dipole moment, but it doesn't flip the magnetic moment. So breaking of the symmetry. So if you apply time reversal, it doesn't flip the electric dipole moment, but it flips the magnetic moment and get breaking of the symmetry. Okay? So the standard model would have the expectation that the neutron should have an electric dipole moment, because time reversal and parity are not good symmetries in the standard model, but we haven't found it. So the effects of the EDM are parameterized by this angle here in this term that mixes. So in the standard model, this the electric dipole moment from the neutron will be generated by the quantum chromodynamics. And so you will add in the standard model Lagrangian basically a term that mixes the electric field of the strong interactions with the magnetic field of the strong interactions. And all we've managed to do is constrain the size of that term to be less than 1 part in 10%. Okay? And this is where axions come in. So if you turn this parameter into a dynamical field, people call it the axion, it will dynamically relax this value close to 0, solving the puzzle of the electric dipole moment of the electron. Now, this particle gets its mass from non-perturbative QCD effects, and for a decay constant of the gut scale, it's 3 kilometers, but if you go to decay constants that are about 10 to the 9 GeV, this becomes like 100 microns, okay? So these are the ones that are relevant for us. It's an excellent dark matter candidate. So we think this setup will be sensitive to axions with decay constant between 10 to the 8 and 10 to the 10 GeV. Now the interesting thing is that this force that this structure would create for axions, you need de modify it because the Broglie wavelength of the axion is different than the neutrino one. Okay, so you need to change the width relative to the length of the structure. Now the interesting thing, the size of the force is about 1,000 times bigger than the neutrino force. So, and that happens mainly because the interaction of the axions with matter is less strong, but there are more of them because they are dark matter. So the number density is high, and that helps give you, I mean, if we are lucky enough that we have an experiment where the dark matter is a background for something else, it's great. So, anyway, but it's a hypothetical particle, and we know neutrinos are there. That's the main difference. And this is rough. If I were to draw the same standard quantum limit line in the plot of the axion coupling versus mass, this is the QCD axion, that's the most interesting one. You see that you can, and I stopped it here because at some point the width of the rods becomes so large, it becomes, I mean, unmanageable, it becomes too large with the Broglie wavelength. So, so that's roughly the range. And with this, I will conclude. We think that the Earth, the fact that it has a tiny weak potential is enough to significantly modify the local distribution of cosmic neutrinos. The same effect that this tiny interaction energy may help us also manipulate it in a laboratory scale. And even though we don't have a concrete idea yet, it's such a challenge, it's such a target. We know the cosmic neutrino background is there. So it sets a target for experiments. Now, and these are going to finish in the most optimistic because I'm talking about tiny forces that we are decades away from measuring. I want to remind people that we've been there before. So if you take atomic clock sensitivity, it continues to prove exponentially. This is Moore's law. This is exponential improvement over time. Okay, so it may take decades, but the detection of the CNUB is more akin to the discovery of gravitational waves. It's an essential part of the theory as we know it. So the moment we discover it, it's going to give us a new tool to look at the universe. And with that, I'll stop here and take your questions. Thank you.
Background to a spot. And the confusion comes from thinking of the context where you have, suppose you have a uniform
distribution.
Yeah. Which is basically thermal.
Yeah.
If you can diffract it to a spot, that changes the distribution function, it would seem to. Then you can run a heat engine between that spot and the background.
Yeah, so this is the part that's very confusing to me. Because we think we can evade these requirements. So it's true if you apply ray optics, I would never see an effect. You can see it directly, but I would never get an effect. The thing that we expect is that you never get a very large effect. The effect, we can never make it more than order 1. In fact, I think once you start getting interference, so this is a linear energy Fermi. So I think that once you start getting higher order interference effect, this will go away. But it's a good question. We think we evaded because of the wave nature of the topic. So there is fine print in Landau when we discuss this exact thing. Yeah, it's an excellent question. I've done checks to make sure that because the structure is periodic, I've averaged over angle. Maybe there's something that I missed. I don't see it because of the wave nature. I keep repeating that, but it is the wave nature. I know, in fact, when we first started thinking about this, we thought we had to rely on the relative motion. And it could be that we still have to, but I don't see it canceling away. And as I said, there is fine print that has to do with the wave nature of the effect and the fact that I can never make it very large. It's always a subdominant effect. Yeah, it's an excellent question. Yeah, I can see it in ray optics exactly where it's coming from. In wave dynamics, I don't see it. And there is fine print in Landau. So yeah, try to average over angles. It would be great if someone could simulate it. Even if we have to rely to the relative motion, the great thing about neutrinos is that the relative motion creates an order 1 dipole. It's not like the CMB where the dipoles tend to the -3. The dipole for the neutrinos is order 1. So it's not a big deal, okay? Yeah, but all I can tell you is I beat myself over the head trying to average over many things. I haven't simulated the whole structure. I just couldn't see where the cancellation would be coming from. Yeah.
So seeing as we're considering building these incredible structures, is it possible to be even more ambitious and actually exploit the dipole and almost make like waveguides directional? I mean, that's what this thing is.
Yeah,
right?
yeah. We
But
thought
like,
about.
it doesn't have to be spherical.
Okay,
Could you make some?
You give me great. I can talk about waveguides because we spend months thinking about them. Actually, waveguides. So there are 2 problems with waveguides. So waveguides in principle are a great idea because if you calculate actually the evanescent wave is 3 meters in dirt, in rock, which is not very dense. But if you go in a metal, this is 1 meter, okay? The idea is, can we take, like, we thought about creating storage rings for neutrinos. So can you just take, like, neutrinos come in, they slowly come in, they bounce around, and then they just go around and you store them, it's great. So 2 problems with that, 2 problems. So one is deadly, the other is annoying. So, yeah, deadly, because, one is the annoying one, is the fact that neutrinos are fermions.
Sure.
So it turns out if you calculate the modes, even if you have many modes inside the fiber, you can only get 1 neutrino in the vertical direction. So that actually tells you that the maximum density you get is not much different than what we get from Earth. Maybe you can get a better graph. The bigger problem, the deadly problem, was the following. So the binding potential is so low that, and these things move very fast. The moment you have a little bend somewhere, they are out of there. So whispering gallery modes, nah. Even for the Earth, I mean, you had to make the thing bigger than the Earth to make things go around. So, like, yeah, it was sad, but it died. So yeah, so not much. I mean, maybe for scalars, maybe for things that interact more strongly, you can do it. But usually, these interaction potentials for dark matter and things are so small that just the centrifugal motion just.
I don't suppose that, well, would be fanciful that some kind of dense accretion disk or something could.
What do you mean?
Like if you had some dense if you had an accretion disk of some kind, but I don't know, black hole, could that effectively?
Oh, okay. Another thing that's my great favorite, and I haven't found any use for it, neutron stars.
Sure.
So in neutron stars, actually, the index of refraction for these guys is order 1. In fact, you have 1 species of neutrinos that doesn't even penetrate the neutron star.
I believe it.
So the question is, can it do anything interesting? and I mean, these are slowly moving, so I don't know if it can affect. The other thing that we haven't found a use for is you have this closed neutron star. Now, if you have some source of low energy neutrinos, and I'm not talking very low energy now, right? Because the potential inside the neutron star is like of order of a few eV. So it's by these standards, it's ginormous.
By the way, these neutrinos are relativistic by the time they arrive at the neutron star.
Yeah, I'm taking that into account.
Yeah, no, of course.
Yeah. So they're
But even then,
they just don't penetrate. I mean, telling you, like dense stuff, it's good.
Yeah. Okay.
I mean, their mass is low, right? So their energy that they carry is a fraction of an EV anyway. I mean, they are semi-relativistic, but their boost factor is not large. So you have a few EV potential, so that's enough, basically, to even the ones that come head-on to just bounce back in some cases. I mean, we haven't done the exact numbers. So, yeah, but, yeah, it would be cool to check. There is something interesting that can happen, but I don't know, because they're the most abundant species of neutrinos we have locally, but there's still very few of them. Like, it's not like they're breaking records here, by any means.
Okay.
Yeah.
Are these structures only specific to the neutrino background, or like the monopole, or could we look for anisotropies in the neutrino background to make asymmetric structures?
So I haven't thought about anisotropies at all. In principle, we think that there should be effects. For example, the biggest one is the dipole motion. And I don't know, you would need precision, right? Now, there is another thing about neutrinos, which is tricky, is because they are non-relativistic, their horizon. Thank you for your question. That was a great question. Because these neutrinos are, as I said, non-relativistic. You have to go. Bye.
Sorry, thanks.
They're horizon, like they haven't traveled a large distance. Like, so it's not clear. I'm very confused about thinking. I know they haven't clustered. Like for 0.8 eV, I'm pretty sure most of the information is erased because they just mix too much with local. Now, the question is, as you become, how much of that information is preserved as they become non-relativistic to be able to extract it afterwards, and what level of sensitivity would you need to get there? So that, I don't know. It's a good question. We haven't thought, we just thought about broad stroke stuff.
Any questions? Thank you again.